In this lesson, we're going to learn about the law of sines. So far, the only triangles we've learned to solve are right triangles. However, in most applications, you have to work with triangles that do not have a right angle. These are known as oblique triangles. The law of sines is the first of two methods we will learn that will help us solve non-right triangles. If a triangle is not a right triangle, then it's either acute or obtuse. We'll show how the law of sine applies equally to both cases. So for instance, if I draw an acute triangle, the only methods that we've learned that would allow us to solve triangles is having a right triangle. So basically our approach is to decompose this triangle into right triangles. So for instance, if I dropped a line from the top, and I could use any of the angles, it's fine, so that it's perpendicular with the base, I've created two right triangles now. We call this line the height of the triangle. Now, in order to work with this, I'm going to label some of the angles in the sides. I'll label this angle capital A, capital B, and capital C. So the angles are being labeled with uppercase letters. Some textbooks prefer to use Greek letters for angles. It doesn't really make a difference either way. It is kind of difficult sometimes to tell when you're writing if you're doing a lowercase c versus an uppercase c, but the context of the problem generally doesn't make a lot of difference. You can work through that. Now I'm going to label the sides of the triangle, and it's important to note that I'm always going to label side A opposite of angle A, side C opposite of angle C, and side B opposite of angle B. So the corresponding sides are opposite to each other. Now, just using our basic right triangle trigonometry, if I chose one of the angles, and it doesn't really matter which one I pick, I could say, for instance, the sine of angle B. Well, we know the sine to be the opposite side over the hypotenuse. So for angle measure B, the right triangle that I have to work with, the opposite side to angle B in a right triangle is H. And the hypotenuse would then be A. So sine of angle B would be H over A. Likewise, if I had chosen angle A, for instance, the side opposite angle A that's in a right triangle is H, and the hypotenuse is B. Now, if I do a little bit of work with each of these, I could rewrite the first so that H is equal to A sine B, and H is equal to B sine A. So we could come up with the height of this triangle using either one of these expressions. Since the height is a constant in the triangle, these two values are equal to each other. So what we can determine is that A sine B is equal to B sine A. Since they're both equal to the height of the triangle, they're both equal to each other. And what I could do then is divide both sides either by the sines, or I could divide by the lengths of the sides. It doesn't matter. I'm going to divide both sides by A first, and then I'll divide both sides by B. So what will happen is A will disappear on this side, B will cancel out on that side, and I end up with sine of B divided by B is equal to the sine of A divided by A, and it doesn't really matter which angle measure and which corresponding side you're working with. So I can also deduce, and I'm not going to go through the proof, but it does work out this way, that this is all equal to the sine of C divided by C. So if you take the sine of an angle measure and divide it by its corresponding side length, then that's equal to the sine of any other angle measure divided by the corresponding side length. And that's what's known as the law of sines. So let me show you the formal definition. It's the law of sines is that the sine of any angle divided by the corresponding side to that angle is equal to the sine of any other angle in the triangle divided by its side. And we generally show that in an acute triangle, but I think it's helpful to understand that this also works for obtuse triangles as well. You just have to do your height a little bit differently. In an obtuse triangle, it's most common to draw your height like this. And I'll label some of the angles here. I'll call this one A, this one B up here, and this one C. And the sides opposites of those, this would be side A, side B, and side C. So what I'm saying here is that this angle measure right here is A. So what that means is this angle measure right here would be 180 minus A. Now, a couple of things I could show here. First is if I take, say, the sine of C, then I have a very definite right triangle that I could work with for that. So the sine of C would be the side opposite to the angle, which is H, divided by the hypotenuse of that triangle. So that would be A. Angle A and angle B, neither of which have a very good right triangle defined with them, but that's why I just came up with 180 degrees minus A. Because the sine of 180 minus A, so this angle that I wrote in, is based in a right triangle. And that triangle is, the sine of that angle would be H divided by C. Now, 180 minus A, if you'll recall from some formulas that we developed earlier in the course, is actually just equal to the sine of A. And you can prove that through the use of your difference angles, difference angle identities. But that is definitely going to be the case. But now, if you take a look at what I have here and here, you can see that these two could be set equal to each other if we solve for H in the exact same way we did the last one. So that means this will work for acute and obtuse triangles. So that's the three different types we have: acute, obtuse, and right. So our standard methods that we learned earlier in the class work for right triangles, and these will work for the obtuse and the acute. In order to solve oblique triangles, you need at least three pieces of information, which could be two angles and one side length, one angle and two side lengths, or three side lengths. If you have these pieces of information, you can probably solve for the triangle that exists. We group these into different cases, and we call these cases either, like in first, we call it angle side angle or side angle angle, which basically means in the first one, angle side angle means you have two angles that are known and the side that's in between those two angles known. Or side angle angle, SAA, means you know two angles and the side outside of those two. If you know one angle and two side lengths, you could be in the side angle side case, which means you know two sides and the angle in between, or the side side angle case, which means you know the two sides and the angle after. or you could know all three side lengths. But one thing to note is that knowing three angles will not result in a unique triangle. There's no way you could solve that. You'd have to know at least one side length. And also, technically speaking, angle side angle and side angle angle are the exact same case. So if you know two angles and a side, then that's the same case regardless. Using the law of sines, we can solve the angle side angle and the side side angle cases. Later we'll learn the law of cosines, which will allow us to solve the side angle side and the side 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 cases. But just to give you an idea of what this all means, the angle side angle means that you know two angle measures within the triangle and the side length in between them. So those three labels that I've put there, those would be the known pieces of information. The side angle angle means that you know the two angles inside the triangle and one of the sides next to those, so not the side in between. As I mentioned, both of these cases are basically the same, because if you the last angle measure, whatever it is, I'll call it alpha, it's sort of a predetermined value because all three angle measures have to add up to 180 degrees within a triangle. So it's already predetermined what that angle measure would have to be, which means you're technically in a case where you know three angles and one side. Same thing over here. So these two are basically the same case. The side-side angle means that you know one angle measure and then the two sides that follow after. The side angle side, you know two sides and the angle in between. And the side 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 means that you know three sides of the triangle. So that's what's happening with those. Let's look at some examples of solving. Solve the oblique triangle with the following characteristics. We have angle A with 78.5 degrees, angle B which is 18.4 degrees, and side A which is 5.2 meters. When they say to solve the triangle, they want you to find all the other pieces of information, all the other sides, all the other angles that are unknown. So let's label what we do know. So we know that angle A is 78.5 degrees. And we know that angle B is 18.4 degrees. And side A is 5.2 meters. So we need to figure out angle C, side C, and side B. Easiest thing to do right now is to figure out angle C. Angle C is sort of predetermined here because all three angle measures in a triangle have to add up to 180 degrees. So 180 minus 18.4 minus 78.5, that's going to give me the value of angle C. So I'll just do this on the calculator. So 180 minus 78.5 minus 18.4, and I get 83.1. So angle C is 83.1 degrees. Now, the remaining two pieces, we're going to have to use the law of sines to come up with. And this is how we'll go about that. So to work the law of sines, we could say, for instance, that the sine of 83.1 degrees divided by C is equal to the sine of 78.5 degrees divided by 5.2. So I've taken the angle measures and their corresponding sides, and I took the sine of the angle divided by the corresponding side. And I set it up to where there was just one variable missing, and that's going to enable me to solve this. So I will start by cross multiplication. So I'm going to multiply these two values, then these two values. So 5.2 sine 83.1 equals C sine 78.5 degrees. Then I'm going to divide both sides by 78.5. I'm sorry, the sine of 78.5. So then C is going to be approximately, I'll get the calculator out here. Make sure you're in degree mode because we're going to be working with degrees here. So 5.2 times the sine of 83.1 divided by the sine of 78.5. And I'm going to round to the same accuracy as the original data. So this is approximately 5.3 meters. So just rounding to the first decimal. So now I've discovered this one. And lastly, I need to figure out side B. Don't fall into the trap of trying to use the Pythagorean theorem at this point. The Pythagorean theorem only works for right triangles. So you can't use the Pythagorean theorem to figure out what side B is. You have to apply the law of sines again in order to figure it out. It's not hard. We just need to get started. And what I'm going to do a little bit differently this time is, since B is the thing I'm looking for, I'm going to put that in the numerator. It's just going to save one small step when you're cross multiplying. So B divided by the sine of 18.4 equals 5.2 over the sine of 78.5 degrees. Now, it may look like I have a choice, and I could use side C to solve for side B, but I'm choosing to use A because if I made any mistakes in the calculation of this 5.3 meters, that's going to then go into the calculation of B, so I'll have a mistake there as well. Rounding errors, if there's any sort of rounding issues, that could propagate. So I'd like to avoid that if possible. So try to use as little as possible any values that you calculated. Try to only use the values that were provided in the problem. So when I cross, I'm basically just going to multiply the other side by sine 18.4 degrees. So B is 5.2 sine of 18.4 degrees divided by the sine of 78.5 degrees, which is approximately, well, find out. So 5.2 times the sine of 18.4 degrees divided by the sine of 78.5 degrees. And rounding to the first decimal, that's going to be 1.7 meters. So this last side over here is 1.7 meters. So now I know the lengths of all sides of the triangle, and I know the measures of all angles. So therefore, I've solved the triangle. The next example, Jeremy wants to measure the distance across a river. He chooses 2 trees on one side of the river and a third on the other side. He takes some measurements and creates the following sketch. How wide is the river? So in case you can't read this right here, this angle measure is 108.8 degrees. And then this one is 25.2 degrees. That one shows up okay there. Now, what we're looking for is this distance right here, which I'll call x, which is the distance across the river, which basically in this case means between the 2 trees, but the trees are pretty close to the bank, so we'll just use that. So how do we figure this out? Well, we want to learn what x is. So x divided by, let me switch to a nicer color. So x divided by the sine of 25.2. That's where I want to start, because that's my missing piece of information and the angle measure that corresponds with it. Then, the only other measurement that I know is the 58 feet. But one thing I could figure out pretty easily is what this angle measure is right here, which I could call alpha. So I could come up with that measure by doing, I'll just write up here. So alpha would be 180 minus 25.2 minus 108.8. And let's get the calculator out and determine what that is. So 180 minus 25.2 minus 108.8. So that's 46 degrees. So this angle measure is 46 degrees, and that's what's opposite the 58 feet. So I'm going to say then this is equal to 58 divided by the sine of 46 degrees. So that x would be 58 sine 25.2 degrees divided by the sine of 46 degrees. And the calculator will come up with that answer for us. Just make sure you're in degree mode. So we can safely say this is approximately 34 feet. So the distance across the river is approximately 34 feet. The next situation we need to work with is called the ambiguous case. And of anything in solving triangles, this is the trickiest thing to work with. You need to always watch out when you have the case side-side angle. Because number one, you could possibly end up with one triangle to solve for. Number two, you could end up with two triangles. Or number three, you could have no triangle possible, depending on the values of the sides and the angle measure contained within. You won't really know until you just start solving. And that's always what I recommend in this case. Just start solving as if there's only going to be one triangle. And, you know, try and prove, it'll show up very readily if no triangles exist. And then just try and prove if you have one or two angles, and one or two triangles. And it's really not that bad once you get started in it. So this is a special situation we could run into when solving a triangle when two sides and the angle opposite are known. We may discover that these values could lead to one triangle, no triangle, or two different triangles. So let me show you with an applet what that might look like. So the situation in the ambiguous case is that you could have for any angle measure that I define A to be, and the side adjacent to it here B, and the side opposite A. This side length, I'm just going to be able to set anything that I want here, because I know an angle, a side, and the side opposite. Now, if the angle measure is something random, say 54 degrees, that's fine. And let's leave this side at 4.07. So I'm going to leave that fixed at 4.07. The problem is, no matter what angle C is, there's no way that I'm going to be able to reach the bottom of the triangle. Let's say it's longer. Let's say it's 9.74. Okay. Now, there is a possibility that this will actually make a triangle. And that's good. Then we have a situation where we can solve the triangle. But what's kind of bad is there's actually two possible triangles that could be defined with that particular set of side lengths. It could be this one, or it could be this one. So there's two possibilities for solutions. And lastly, let's say that the side length is something like 12.5. Well, we could make a triangle here in this direction. That could make a triangle. If I swung this point around, there's no way I could reconnect with the other triangle. So there's actually only one triangle that is possible in that respect. So depending on the angle measure, the height of the triangle, and what B is, different values of A could lead to different possible types of solutions. It basically comes down to if A is less than the height of the triangle, so even if I made it like 8.5, if A is less than the height of the triangle, there's no way it's going to reach to the base of the triangle. If A is somewhere between the height and B, then it'll work out that I can come up with two different triangles. But if A is greater than this side B, then I could only have one triangle. So there's different possibilities that could exist here, and this applet's kind of nice to at least help you visualize exactly how those would work out. So let's try and solve some examples using the applet to kind of guide us along. So let's solve the oblique triangle with the following characteristics. Angle A is 42 degrees, side A is 18.7 centimeters, side B is 12.5 centimeters. So if I were to work this using the applet, angle A is 42 degrees, so I'll just kind of change this point till I get about 42 degrees. Side A was 18.7 centimeters, so I'll make this 18.7 centimeters. And side B was 12.5 centimeters. All right, and since this is a little bit long, I can actually kind of move. If I press Shift and drag the mouse, I can move things around. Or if I scroll in and out, I can zoom in and out to kind of make the figure work better for me. Okay, so this is a potential triangle, but I would need this side to kind of come out a bit and reach about right there. And when it does, that would make a triangle. And if I swing the other direction, it should make sense that I can't get another triangle there. So I should only get one solution to this. So let's solve the triangle and see what happens. You don't need an app like that to actually work these through. You can just use what we've learned with the law of sines, and you can figure these out otherwise. So let me show you what's happening. So angle A is 42 degrees. Side A is 18.7 centimeters, and side B is 12.5 centimeters. So I have an angle and the two sides that are adjacent and opposite to them. So the case that you'd like to be in is two sides and the angle in between. But it's two sides and another angle. This is the ambiguous case. Let's just try and solve. Let's see what happens. So let's say I want to solve for side C first. Well, that's going to be a bad choice because if you'll notice, I don't know side C and I don't know angle C. So let's not go that route. Let's try and solve for angle B. And this should work out okay. I would have to do the sine of B divided by the side length that it's opposite, so divided by 12.5, equals the sine of 42 degrees divided by 18.7. So I can solve this by multiplying both sides by 12.5. So the sine of B is going to be 12.5 sine 42 degrees divided by 18.7. So the sine of angle B is approximately, let me get out the calculator to check this out. Turn that on. Clear. We're in degree mode. Make sure you're in degree mode, but we've been working with this already. And then divided by 18.7. So we get 0.4473 basically. And actually, you know what I'll do is I'll say 4472 and then put some dots on here because I don't want to round at this point. Anytime you round, you introduce error, so I'm going to avoid rounding. So basically what I'm going to do at this point is just take the arc sign of that number. And these dots are basically just telling me that I'm using the whole value that's shown in the calculator. So I will do second and sine, which gives me the arc sign, 0.4472. And so to the nearest integer is what I'll use since that's what my other angle is in. I have 27 degrees. So angle B is about 27 degrees. Now, the thing that could happen is if you didn't already know that you were only going to get one triangle out of this, the thing that could possibly happen is you could have another angle measure that was 180 degrees minus this. So you could say that the angle B could be 27 degrees, or, let me get rid of the calculator, 180 degrees minus 27 degrees, which is going to be 153 degrees. So the problem with that, and this is always how you're going to figure out if you have that second triangle or not, but the problem with this 153 degrees is that if you add it to 42 degrees, that's going to give you 195 degrees. That's already larger than 180 degrees. That doesn't leave anything for C. So you can rule out that that is a potential. So we can throw that possibility out. Now to figure out what angle C is going to be, we need to just do 180 minus 42 minus 27. Get out the calculator for that. So 180 minus 42 minus 27. That's 111 degrees. And now we just need to figure out what side C is. So side C we can come up with by doing, say, C divided by the sine of 111 degrees is equal to 18.7 divided by the sine of 42 degrees. So C is going to be 18.7 sine of 111 over the sine of 42. So we get out our calculator. So 18.7 sine of 111 divided by the sine of 42. So 26 degrees, or not degrees, 26 is the length. And that should be to the first decimal. So 26.1, and I believe that was in meters. Nope, centimeters. So 26.1 centimeters. Now we have all pieces of this triangle solved for. All right, next up, solve the oblique triangle with the following characteristics. 120 degrees for angle A, 123 for angle A. Side A is 5.3 centimeters. Side B is 8.8 centimeters. Now, I'm not going to use the applet. We're just going to let this guide us and try and figure out how this works, because you're not going to have the applet for the test. Feel free to use it in your homework to kind of visualize what's going on, but in the test you need to be ready to do it without the applet. So let's solve for B first, angle B. So the sine of angle B divided by 8.8 is equal to the sine of 123 degrees divided by 5.3. So the sine of angle B is going to be 8.8 sine 123 divided by 5.3. Not degrees, just 5.3. And let's see on the calculator what that comes out to be. So clear everything I had before. 8.8 sine 123 divided by 5.3. And I've got 1.3925. The problem with that is all sine measures are the values of sine have to be between -1 and +1. So when I try and do an arc sine of this, I'm going to get a domain error. So what that means is no such triangle exists. Okay, and you can use the applet to show. Next up, solve the oblique triangle with the following characteristics. B is equal to 80.1 centimeters, C is equal to 66.2 degrees, and the side C is 74.1 centimeters. All right, so the length of B is 80.1, angle C is 66.2, and side C is 74.1. Now, in order to solve this, we have to assume a triangle exists. So let's just try and figure out, in this case, we'll solve for angle B first. So the sine of B divided by 80.1 is going to equal the sine of 66.2 divided by 74.1. So B is going to effectively be the arc sine of 80.1 sine 66.2 over 74.1. So if I put this into the calculator, I'll do arc sine 80.1 sine 66.2 divided by 74.1. And I get 81.5. I'm going to need to round to the nearest first decimal place, just to match what's in the calculator. I'm sorry, just to match what was originally given. So angle B should be approximately 81.5 degrees. The thing about it is if I take 180 degrees minus that, which this is always just, this is what your test is going to be, then it could also be 98.5 degrees. And the reason that it could possibly be that is, if you'll notice, if you take 98.5 degrees plus 66.2, that's 164.7, which is less than 180. So there is going to be two different triangles that we can solve for. So that's not a big deal. There's more work involved, but it's not hard. So we just come up with the angles and we say, all right, so triangle 1 for triangle 1, we have angle B set to 81.5 degrees. So then we need to figure out what angle A is. So angle A would be 180 minus 81.5 minus 66.2. So on the calculator, let's see what that is. So 180 minus 81.5 minus 66.2. So that's 32.3 degrees. For triangle 2, we're using B as 98.5 degrees. We just do a similar thing. We still need to solve for angle A. We're going to do it in the exact same way. So 180 minus 98.5 minus C, which was still 66.2. So this would be 15.3 degrees. So now the last thing that we would need to solve for in each one of these is side A. So to get side A, we need to take A divided by sine of 32.3 degrees equals, and then just use some original known information. So I'm going to take 74.1 divided by the sine of 66.2. And both of those were known originally in the problem, so I'm going to use those. I'm going to capitalize on that knowledge. Over here, it would look like A divided by the sine of 15.3 equals 74.1 over the sine of 66.2 degrees. And then you just use the calculator to solve each one of those. So just plug them in real quick. 74.1 sine 32.3 divided by the sine of 66.2. And we get 43.2, or 43.3 when we round properly, that is. And I believe that was still in centimeters. And then for the other triangle, we just do the same thing. I'm going to hit second and entry. The only thing that's changing is this angle measure, so to save me some typing, 15.3. So 21.4. So A equals 21.4 centimeters. So those are the two triangles that are possible. The area of a triangle. A common formula for measuring the area of a triangle is area equals 1/2 base times height. But if you don't know the height of the triangle, but knew the two side lengths and the angle between, then you could find the area of the triangle using 1/2 BC sine A, or AB sine C, or BC sine B. It doesn't really matter, as long as you're using two side lengths and the opposite side. So that works in both the acute case and in the obtuse. So if we draw the height of the triangle, we can say here that the area we know to be 1/2 of the base times the height. Now, since it's 1/2 the base times the height, in this particular triangle, I have the base as C. So the area is 1/2 C times something. The height of the triangle, what we'd have to do is say, for instance, sine of angle B would be the height of the triangle divided by side A. So A sine B is the height of the triangle. So we can replace that with A sine B. So the area is 1/2 of AC sine B, basically. So you take two sides and then the angle in between them. So let's find the area of the following triangle. So we would take, so area would be 1/2 of the two sides multiplied together times the sine of the angle in between. And it has to be the angle in between them for this to work. It doesn't really matter if you're calling them A, B, C, or whatever. It just has to be the two sides and the angle in between those two sides. So the side angle side case is what we're working with. When we plug this into the calculator, we have, say, 0.5, let me clear this out, 0.5 times 12.75 times 15.21 times the sine of 32.5, and that means this area is approximately 52.10 square meters. Since we're measuring area, that needs to be squared units.